All right, so last time we left was this argument about consistency of theory. It seems like the empirical observations in the previous paper we discussed contradict with the statistical learning theory. So the authors in this paper, I think, provide a very good intuitive understanding of why there is actually no inconsistency, and the consistency really arises from misunderstanding. Right, so the major misunderstanding are from two aspects. I think the first aspect is this: people tend to think that the hypothesis space complexity is small, implies generalization gap is small, also means that generalization gap small implies the hypothesis space complexity is small. It's not true, right? We're simply getting the upper bound. Saying the upper bound is small might suggest that the quantity is small, but the quantity is small doesn't imply that the upper bound has to be small, right? And in fact, upper bound can be arbitrarily large, depending on how good the upper bound is. So, some of you might argue, well, if that's the case, then, how can we trust this statistical learning theory, right? How can we trust these bounds? And indeed, in our textbook, there is, Mori, the author of our textbook, derived a lower bound on the generalization gap by showing the existence of a bad distribution that kind of characterize something called U here. So let's see, what is U? In a set of U all of all possible problem configuration, there exists a subset U, such that the generalization gap is small also implies that the hypothesis space complexity is small in U. So essentially what people are really showing is a lower bound. Okay, so we've seen upper bounds. Now, Mori in the textbook, actually section 3.4 showed a lower bound. So what does that mean, right? So if there is a lower bound, does that, basically people say, oh, maybe this is just means that it's a tight characterization of the generalization gap. But actually that is not quite true. And the major discrepancy between the statistical learning theory and what we observe in practice is that in statistical learning theory, you often consider a set with uncertain probability, or underlying probability, also uncertain sample, right? So P of X, Y is something that is coming to a set that is, you don't know much about it. Also the S, the sample that you observe is also something that is uncertain, right? Whereas in practice, oftentimes you have a fixed underlying distribution. Also, usually you observe the training data set, the training data set, which is the sample, right? So in that scenario, like what Kenji was saying in his paper, you have a set versus a point in that set. Whereas statistical learning theory is trying to characterize the properties of that set. That's why they have like this hypothesis complexity, a hypothesis set complexity and so on. Whereas in empirical observations, people often are only concerned about a specific data set and a specific underlying distribution. And essentially that's why there's this discrepancy in terms of understanding statistical learning theory, right? Like in the second bullet point here, however, if the problem instant at hand is not in such a U in the proofs, so basically means that we're not in the worst case scenario, right? This is not a worst case scenario that we're working with in practice. So basically generalization gap is small doesn't necessarily mean that the hypothesis space complexity is small. Okay, so does that make sense? So basically, it is naturally possible that the generalization gap is small with large hypothesis space complexity, instability, non-robustness, and sharp minima. Therefore, there's no contradiction or paradox. Okay, so I think that most when I was reading this paper, the biggest, in my opinion, I think the biggest contribution of this paper is to clear out a lot of confusions in these terminologies and in the subtleties in terms of understanding statistical learning theory and how it compares with what we observe in practice. So I think this is the most interesting part of the contribution of this paper. Right. So so the first theorem of this is basically trying to characterize an open problem, right? I didn't put the open problem here, but you guys, everyone has access to the paper. Basically, the open problem is that you wanted to tightly characterize the expected risk of a generalization gap, right? So either the risk or the generalization gap for a hypothesis F that you learned. But also, you wanted to have you wanted to tightly characterize the expected risk or the generalization gap with a sufficient complex deep learning hypothesis space. Basically, wanted to produce theoretical insights in distinguishing the case, because this is basically with respect to the previous paper of this random label stuff. Random tests in that paper. So they were saying that you wanted to produce theoretical insights and distinguish the case of natural problem instances from the case of other problem instances, such as image with random labels. So you wanted to distinguish images with random labels from images with natural labels. So the theorem 1, it is a linear model, first of all, but even linear model, the results are kind of very interesting here. So what are we trying to say here? First, let me highlight, I think since everyone has already read the paper, I'm gonna just highlight a few things I want to say here. First of all, this hypothesis, this if condition here is trying to tell us that this is a over-parameterized scenario, okay? Why is that? Okay, I don't know why my highlight would, I think you couldn't see anything if I highlight things. So I'm gonna just do this underline. Any ideas why this is an overcomplete scenario for this linear model, right? So what is the linear model? A linear model is nothing but, a feature matrix of the training input, phi, multiplied with omega, omega being the linear model's parameter, okay? So what this is saying, n greater than m, right? And rank of the phi greater than equal to m and rank of the m smaller than n. This basically means is a over complete scenario, okay? And from that, what they were saying here is that the hypothesis space of the over parameterized linear model can memorize any training data. Why? Because for any y in, for any matrix y, there exists a parameter omega prime such that the y hat of omega prime is y, okay? So basically this means that for anything, you can memorize it so that the training error is 0, right? So this is what it means. Also, if you look at the second claim here, the second claim says that it decreases the training and test error arbitrarily close to 0. So, the epsilon could be really small, and this Frobenius norm of these two matrices are pretty small as well, smaller than 1. Now, if that's the scenario, what this means is like bullet point A is saying the training error can be very small, very close to 0. Bullet point B says that the test error could be arbitrarily close to 0, right? But what's surprising here is that bullet point C says the norm of the parameter being arbitrarily large, right? So the Frobenius norm of the omega being greater than delta, and also more importantly, this omega is arbitrarily far away from the ground truth parameter. Any insight or question about the theorem? What is theorem saying? It seems to be a very pessimistic result, right? It says that, if you have an overparameterized linear model, it can actually memorize any training data, even for a linear model, not to mention a nonlinear model. And it decreased the training and test error arbitrarily close to 0. However, it is different. The model that's actually decreased the training and test error arbitrarily close to 0 is actually arbitrarily far away from the ground truth parameter, as long as you can make the norm of the parameter being arbitrarily large.
It seems like you need to regularize the parameter.
That could be, but I don't think that's the message here, though. Right? It doesn't mean that when the parameter is regularized, it will be okay. Like it will converge to the true parameter. So if you read the paper, I think the paper actually says that normalizing the norm is not useful. Okay, so I didn't have like the results following this theorem 1, but if you guys look at the paper, I don't know, maybe I shouldn't do it in class because I wanted to finish talking about this paper as soon as possible. But if you go back and look at the paper, you will see the authors do not suggest that if you regularize the parameter, the norm of the parameters, it will be fine. Okay, we'll see that. So indeed, what the message here trying to say is actually, I think, what Kenji really are trying, and the authors, co-authors really are trying to say is, they were trying to point out that traditional statistical learning theory has a fundamental flaw in terms of characterizing a generalization, the true error or a generalization gap for a specific hypothesis we find in a hypothesis set. And the reason is we're characterizing an upper bound on that hypothesis. Upper bound of that expected error of that specific hypothesis through a collection of hypotheses, which is called the hypothesis class. So he's simply saying, because this way of characterizing generalization error is very pessimistic, because you can always have a worst scenario, such as, what you might say, a bad scenario that makes the generalization error really large. But oftentimes in practice, you don't encounter such worst scenarios. What you encounter is a specific scenario that right? You observe the training data sample. You observe as, there is a specific underlying distribution. You might even have some prior knowledge about it. Right? So under those scenarios, yeah, I agree. Statistical learning theory doesn't really help you because there might be some worst scenarios that is not representative of what you should be observing in practice. Okay, so what this paper is really trying to say, later on we'll see that they were able to find a bound, or not a bound, a equal, like a way of characterizing generalization error without an upper bound. So this is the contribution, but of course, there's no free lunch here. And we will talk about why, although this seems to be a very attractive result, there are some drawbacks associated with it, okay? Right, so I wanted to first talk about one thing that everyone does, which is the cross-validation, right? So everyone, ever since you learn machine learning, maybe the first 2 lectures, you've started to understand what is a cross-validation after you learned what's a, classifier, right? Cross-validation is really widely used, and everyone basically report their results based on cross-validation, right? Then, what the first contribution, of course, no, not the first contribution. I guess the first contribution is to, clear out confusions about statistical learning theory and what we observe in practice. So that's the first contribution of this paper. The second contribution of this paper, which is also very interesting, is to give a so-called non-vacuous generalization bound using validation. Well, so in my opinion, I think what they were really doing is, instead of, trying to upper bound that generalization gap using a hypothesis class that has to be independent of the sample S, here they were actually saying, I can use a hypothesis class of like validation models. So we'll see what this is really doing. Proposition 5 is the example of generalization guarantee using validation error. It is actually a very simple application of the generalization gaps we've seen in Maury's book. But here we can see, they assume the way how they construct that generalization error is kind of interesting. So they started with S, M, val. What is that? That is simply just the sample of the validation. Okay, so it's generated by IID drones according to a true distribution, right? So nothing but you can think of it as a sample from the validation set. So now what is really interesting here is that they define this kappa Fi. So kappa is a way of characterizing the difference between the ground truth error, the expected error, R of F minus L of F XIYI. So L of F XIYI is nothing but the empirical loss evaluated on this example X1, XIYI. Okay, so XIYI, of course, is coming from this validation set. This validation, the number of examples you have in the validation set is denoted by M sub val. So that's the number of examples you have in your validation set. Okay, so there is a very strong assumption here. Suppose that expectation of these kappa squared is upper bounded by gamma squared. Also, the absolute value of these kappas is upper bounded by a constant C. However, if you consider a scenario where, you can consider a very bad scenario of kappa being very large and C being very large, but the truth is that kappa cannot be very large. If you look at, I won't go into the details here because it's all in the paper, but what they were trying to say is even under a worst scenario, the gamma and C are reasonably, has a reasonable value. Okay, so suppose that you have these upper bounds almost surely for all F and I. So what is F? F is any model, or you can say any hypothesis within your validation set of models. Okay, and I is the number, the index of the example in your validation set. So of course it can go from 1 to M val. So if that's true, then for any delta with probability at least 1 minus delta, the following holds, which is the generalization gap upper bounded by this term here, by these 2 terms here, right? So there's 2C multiply with logarithm of the cardinality of F val. Of course, the paper also has a way of using Rademacher complexity of the validation set rather than the cardinality of the validation set to denote the complexity, but the idea is very similar, right? You can imagine that we can, we also did something similar when we jumped from finite hypothesis class to infinite hypothesis class. So anyway, I think the major takeaway message I wanted to say here is that we're kind of transferring, the complexity of the hypothesis class into the complexity of the validation class, right? So it's like there's still no free lunch, but somehow by doing this transformation, you were able to more tightly characterize it. We'll see what it is, right? For example, before that, I want to just mention that the bounding proposition 5 is non-vacuous and tight enough to be practically meaningful. So this F-val here is the defined as a set of models that is independent of a held out validation data set, right? So you can depend them on the training data set, but it has to be independent of the validation data set. However, the model is of your own choice, right? So you can try to choose your validation set of models. So why, this is a non-vacuous bound? Imagine, for example, if F-well can contain a set of models that each element F is a result at the end of each epoch during training with at least 99.5% training accuracy. In this example, this cardinality of the F-well is almost the number of epochs multiplied with the cardinality of the set of possible hyperparameter setting. It's likely to be much smaller than that because of the 99.5% training accuracy criteria. The fact that the space of many hyperparameters narrowed down by using the training data set as well as the other data set from different tasks. So also, the paper had a very interesting analysis about what is the largest C you can have, which is the largest gamma you can have, even in the worst scenario. If you have more than enough number of training validation examples, then these bounds can be non-vacuous, right? So which is very interesting because a lot of bounds are actually vacuous. The previous bounds that are concerning the complexity of the hypothesis class, concerning the instability and stuff like that, are many of them are vacuous. But this, you can use validation, which is a very, very simple idea. And a lot of us, almost everyone of us is using it every day to characterize the generalization ability of neural networks. Okay, so that's the contribution I think is very interesting. It's like providing a theoretical support about why we do cross-validation, right? Why would the test accuracy, the validation accuracy we see as a good representation of the test accuracy. Now, the algorithmic contribution, or I guess the most important contribution of this paper, is the so-called direct analysis of neural networks. It's not an upper bound, but a tight equality, right? So, this is like a theoretical insight while tight theory for every pair PS. So P is the underlying, distribution of the input examples, and S is the sample. As I mentioned before, the main difference between the empirical observation and the statistical learning theory, the traditional statistical learning theory, the major difference is that statistical learning theory was considering a set of this PS pair, whereas in practice, you're looking at one PS pair, okay? So that's the major difference. Now, so here we, Kenji kind of put this open problem too, that tightly characterize the expected risk or the generalization gap of a hypothesis with a pair, PXYS, of a true distribution in a data set, producing theoretical insights based only on properties of the hypothesis F and the pair. Okay. So this is a very interesting result. The notations can be a little bit confusing, but really, this Z, okay, so let me try to mark here. Yeah, you have the pre-activation vector of the L hidden layer, right? The width is N sub L, and then the ZL is just the pre-activation vector, right? Of course, ZL would have this recursive definition here because it is, through a ReLU activation and then a linear map, you get this activation, you get the pre-activation vector here. But what's really interesting is that Kenji have introduced this notation here. So the maybe we can say dot of sigma. Yeah, so basically what this means is that, you know, instead of doing this thing of like, you know, doing a RALU activation over all element-wise RALU activation, right? So this is a vector here, right? What I do is I'm gonna just rewrite this entire thing as this notation here. So what is this notation? This is element-wise product. So what this means is that, you know, this vector will be considered as a element-wise product of each element in these two vectors. So this is one vector, this is another vector. This vector denotes, you know, I'm going to activate, right? So the RALU is, you know, either multiply with 0 or multiply with 1. So activate, or inactivate or activate, right? So the dot of the sigma basically says that I'm, you know, going to have a bunch of a vector which is zeros or ones, and doing this is an element multiplication with this vector. Okay, does that make sense? So basically you just wanted to write it in terms of this way. It's just a way of writing things out. Then, you know, what's really interesting is that because of this notation, because of the convenience of this notation, we can write the pre-activation vector of the else layer, which is the last layer, as this form here. So it's very interesting to notice that this W bar here is nothing but a product of the weights along the path from the input example to the output neuron K. Okay. So this is the J0. It just means that this is the J0's element of the input example or input factor. Now this K here means is the K's neuron. Okay. So this is any path. Imagine that you have a neural network, right? You have fully connected, you know, layers. So what is, can you imagine how many paths are there? Right? Yeah, so let's say all of them have width n. So what is the path, you know, number of paths you can imagine there are, you know, connecting from here, like this is J0, here this is K. Also there's, say, the number of depth, the depth is just L. M power depth, yeah. Exactly. So it's basically M power depth. But of course, you know, if you have different, you know, width, then it's just a multiplication of the width, right? Along all the layers. So it is actually, you know, you would say it's exponential in terms of the depth, right? So that's one thing that we have to keep in mind. Now, what is this other function? This other function is the activation function, right? So we have these activation vectors. So this is basically saying the activation vector multiplied along the path from the J0 to K. Okay, so does this make sense? Because of the way of conveniently writing this in terms of this element-wise product, we have a way of compactly writing the output Z in this form. Okay, so this is one, I guess, you know, big insight or big novelty of this paper, right? So it's to have a convenient math notation to denote the final result before the activation at the last layer. Okay, so once we have that, let me go to the other one. Yeah, so once we have that, you know, what we're saying is like, you know, the model description using this deep path, we can just merge the indices J0 through JL-1 into J with some bijection between these things, right? It's hard to spell it out, but basically it's a merging the indices into the indices, you know, so you have this indices to indicate the path, but you could just, you know, order them so that, you know, you can just use the order to, how to say this? Yeah, you're just saying, you know, the first path is 1, the second path is 2, rather than using a sequence of the things to denote the path, right? So you just give them an identity, basically, give them like a order of these paths, right? I hope this is understandable. It's hard to explain here, but you know, basically this is just a bijection between using this to denote the path versus just using the number of paths and, you know, the integer numbers from 1 to the total number of paths to indicate the path. Right, so once you do that, again, since will be even simpler, right? You can simplify the entire thing into this notation here. Notice that this sigma bar is indicating, again, similarly as what you observed before, the activation along the path, right? So if anything is not activated, then it will be 0. But if it is activated, every path is, you know, I would say, how should I say this? Every ReLU activation is activated along that path, then it is activated, okay? You can see it's rather sparse, actually. So X bar also represents, so let me see, so, you know, this W bar and X bar represent you basically is like, instead of having this very complicated way of indicating the path, they were just using the J here. So that's what they were saying here, right? Right? And instead of using them as capital W bar, they use a, you know, omega bar here. And instead of using sigma dot, they use a sigma bar here. Okay. Okay, it's just a change of notation, but very importantly, we need to notice that this sigma j represents summation over all paths from the input to the case output unit. Okay, so once we know that, then essentially everything becomes very compactly represented, right? So, you know, this ZLXW is just summation over this L prime from 0 to L-1, this omega and the sigma, and the Z from L prime, okay? Right, so L prime can be anything here. And this essentially is, this was skip connection. Right, once you have skip connection, you can also see that finally, it is the same as without skip connection, you can still write it in terms of this form. So you get a uniform representation of this unit, case unit, before activation at the Lth layer. Okay, so everything is still the same compared to the previous slide. Now, finally, you know, we wanted to introduce a bunch of notations here. So, but I guess right now those notations don't mean anything to you yet, but let's directly look at Theorem 7. So Theorem 7 says that this generalization error gap, okay, minus this CY, we'll see what CY is actually here, but we'll explain it later on. It has an equality. So what's really interesting about this result is that it's not an inequality, although there is an inequality here. But overall, this is an equality here. So this is basically a tight characterization of this generalization error gap, right? R is the true error and this is the empirical error. And this CY is actually defined as something like this. So we'll see what is CY. So can someone tell, maybe we can have a discussion about this. What is CY here? We've learned about concentration inequalities. What's CY here? It's measuring the concentration of this guy, right? Yeah, when I say concentration, what do I mean? Recall your concentration inequality there, right? Someone's saying it's the difference between ground truth label and our data. Is that true? The ground truth label and our data? What is our data? The YIs are already the label of the training examples, right? XIs are the feature vectors. Yeah, so this is measuring the concentration of this. Okay, so what is the expectation of Y here? Expectation Y actually, is related to your underlying probability. Okay, so what is really nice about this is that I don't really tell you how to characterize it because you don't know the underlying distribution. But somehow I'm telling you, as long as you know it, then this is how far, what's your gap. Do you see what I mean? So what I really mean is that I cannot compute it, right? You might be able to have a concentration inequality to upper bound it with some probability, but the truth is you cannot know what is the real value of this. Okay? So, what this Theorem 7 really is saying is that, again, I want to say there is no free lunch here. Why? Because I'm still not getting an equality. Although it looks like I'm getting an equality, but this quantity, I cannot calculate it. I have to use like a concentration bound to bound this deviation, right? The CY, with high probability, the CY will be smaller than equal to some quantity, which is related to like, by precision, related to the delta and so on, but it's gonna be a upper bound of this guy if I wanted to characterize it. But the way that the authors write it this way, you cannot argue that this is not an equality, right? This is indeed an equality, but it's just that they're hiding these uncertainties here. Our uncertainties about the underlying distribution here. But still, the result is very nice because it is for a specific PS pair, but not for a set of PS. So this is very important. Now, that's our understanding of the CY. Okay, any questions? Okay, also there is this cosine of theta of the omega ks. So what is the cosine of theta omega ks? What is theta omega ks? Is the angle between V and omega k bar. What is V? Go back to this. What is V here? is again a concentration, right? It's the concentration of Y, K, and Z. So what is Z? Z is your output, right? Output before activate. I mean, you can think about it as the output of your neural network. And Y is what? Ground truth label. Yeah, so you're measuring the concentration of how good Y, K, and Z
Can I ask
fit.
why is this concentration?
The concentration because you're measuring like the empirical expectation and the actual expectation.
But why is that a
Empirical
concentration?
mean and the actual expectation.
Why is that a concentration? What does this have to do with concentration?
Okay, I'm gonna ask you guys, why is that a concentration? Anyone has an explanation? Okay, Michael, do you want to just say that? Say what you typed in the chat?
It's just the thing that a concentration bound tells you will be small with high probability.
Right. So does that answer the question? I mean, Mike to Mike, Michael Curry to Michael Rossum.
I'll think about it.
Okay, so this, the understanding of the theta is really like, it is characterizing. So first of all, let me understand this eigenvalues of G and V measures the concentration of the given data set S with respect to the unknown probability X, Y in the space of the learned representation Z. Does that make sense? Yes, you are observing from the expected value and the sample mean from your samples, right? So anyway, so I think that's something we've already talked a lot about when we talk about concentration inequality. So we can see here the benefit of deep learning from the viewpoint of deep depth feature learning. Even if a given S is not concentrated in the original space, concentrated, so, you can still optimize omega such that it concentrated in the space of the Z. So that's like the nice thing about, about deep learning here, really an understanding of why deep learning help us to get a better generalization performance, right? Similarly, the CY is measuring the concentration of the Y L2 norm squared, right? As I said. So also the cosine theta term measures the similarity between this bar K, between this and these concentration terms, right? Because it's between the V here. V is essentially the concentration terms here, okay? So, yeah, I don't know. I mean, are people confused? If you read the paper, it should be rather straightforward, but I don't see any questions. I wonder if people have actually read the paper. Okay, so I'm gonna ask a question. You know, I said Theorem 7 is nice, but there are some drawbacks. And I kind of hinted it by saying, you know, the path is very large. The path is, there are a lot of paths that's essentially exponential in terms of the depth. And I also hinted that you don't know this concentration terms because you cannot evaluate the expectation. You only get a sample estimation, like, you know, 1/m summation of these terms, but you don't get to estimate this expectation here. So maybe can we have a discussion about what are the drawbacks of this work? Or, you know, is this already solving everything we need to do about generalization in deep learning? I mean, should we have a breakout room or something? We only have 35 people here. Maybe we can just break people out in 7 groups. How do I?
Could I get assigned to another breakout room? I was the only one in
I
mine.
just did.
Oh.
I assigned you to room 3. Okay, anyone want to share what you discussed in the breakout room?
In our group, we weren't quite sure how easy it would be to calculate these, like the maximum eigenvalue, or perhaps the maximum eigenvalue might be rather large. And so this bound might not be ideal always. We weren't sure though. We would like to hear thoughts on that.
Okay, great. Any other ideas? Was the eigenvalue only the concern? Let me ask you a question. Are you really able to calculate the eigenvalue?
Probably not, right?
Yeah, why is that?
It's a very large matrix, and it's based on the outputs of deep learning models.
Mm-hmm. So let's first see what is G here, okay? Let's understand G better. G is defined here. Can everyone see this? So I'm gonna ask you, how do you calculate G? If you if to calculate G for me, how would you do that? Notice that you don't know Pxy, right? This is unknown. How would you do this? Any idea?
You can use a concentration bound somehow. Is that?
Yeah, you can use a concentration bound, but it's gonna be a high probability bound for this quantity, right? Only with high probability, you know, this quantity is upper bounded by something, but you cannot compute it exactly. Do you agree? Because, you know, even with high probability, there is still a small probability that the quantity will exceed that.
Right.
Right.
So should here G converge to the zero matrix?
Yes. Yeah, concentration bound, that's the idea. Well, however, what you can do in practice is that, you know, if you get a concentration inequality for this G, you kind of get an upper bound, you know, G smaller than some upper bound, smaller than equal to some upper bound with high probability. Okay, so I'm gonna ask you, can you also transfer that high probability bound in here? I'm gonna erase everything here. Okay. Can you transfer that high probability bound here? What I mean is, like, you know, you don't know exactly what is G, right? So you can get an upper bound with some high probability. Now, you know that this quantity depends on G, but, you know, like I said, like you guys said, we don't know what is exactly G, but we know with high probability, G is something smaller than that. Then can you say that this thing would be upper bounded by a quantity related to that, and a quantity and the probability related to the concentration inequality you used to characterize G? You can, right? So that's the idea. Basically, you know, you essentially what this is saying is that you still have an upper bound, but this upper bound depends on the concentration inequality for the G here, okay? Of course, you're not directly doing G, you have to calculate the eigenvalues of G, and essentially things become much trickier there, because if you consider the eigenvalues, right, how robust is it in terms of the, you know, the differences in G? Like if you have a small difference in G, will the eigenvalues be vary a lot, right? You need to characterize so-called sensitivity of these eigenvalues with respect to little changes in G. So that's why this paper didn't talk about these issues, right? It is talking about, you know, I can give you a, you know, upper bound, or no, sorry, my bad. I can give you an equality, which is, it seems like tightly characterizing this generalization error, but it doesn't talk about how you evaluate all these quantities in this equality. Okay, so that's the first difficulty here. Now, what is the other difficulty? Has people thought about other difficulties? You know, for example, how would you calculate this norm here? Think about the computation complexity. How do you want to speak of? Since I know that you looked at this paper before.
Actually, I didn't read this paper before. I think I'm looking at a different paper.
Okay, fair enough. Anyone else wanted to say?
In our group, it was
okay.
That there are a lot of paths. So unless you have some way of getting rid of some of them early, that gets exponential.
It's very expensive to calculate the norms, right? Because there are so many paths out there. You know, to calculate them is very expensive in terms of the depth. If you have a really deep neural network, this is just very computationally prohibitive, right? Exactly, that's another concern we might have. Anything else? Any other, you know, insightful discussions in the breakout room? There's only my baby screaming in the background. No? Really?
So I was wondering something.
Okay.
Does this bound match empirical computations?
What does that mean? Empirical computations? Oh, you mean like the previous paper we talked about?
Sure, any of those test curves.
I don't know. I don't know whether it matches the test curve. That's a good point though, right? So whether it actually matches what we observe in test. But I'm gonna talk about another paper today in generalization, which is related to compression, which actually gives us some good, you know, matching with the empirical error or empirical observation of the test error, but it could be non-vacuous. Yeah, Chen Chen, do you say something related to the true distribution? Do you want to speak up?
I said that because you mean the eigenvalue of G's actually cannot be computed exactly.
Yeah, okay. So this is related to what we were talking here, right?
Yeah.
We're talking about, you know, we essentially have to transfer these things into concentration inequalities and get a high probability bound in the end. So still, it is not going to be a actual equality.
Yeah.
But the good, you know, of course, I don't want to, you know, say this paper is not, you know, the contribution is not very impressive. I won't say the contribution is really, really nice. You know, it actually tells us how to look at a pair of PS rather than look at a set of PS, okay? So actually, I wanted to say that another concern I have are essentially the sensitivity of the eigen values, right? So, you know, we are talking about the L2 norms of these, we're talking about the eigenvalues. We're also, but here we're talking about the G's, right? So the concentration is on the G, but the eigenvalue, how does the eigenvalue change is another story. So we're far from understanding this bound exactly yet, right? We need to do a lot of work to understand this bound better. For example, understanding how the eigenvalues would change, right? How the eigenvalues differ when you have a small perturbation in your G matrix and so on, okay? So that's what I wanted to emphasize here. Rather, you know, in addition to this concentration inequality we have to use to get, you know, a good, to get a realistic computable bound, okay? So that's everything I wanted to say about this paper. I mean, I hope after we review this, we clear some misunderstanding about statistical learning theory. We'll clear why there is a discrepancy between theory and practice. We'll understand that validation is actually a very powerful tool. And we know that from a theoretical point of view that it is a powerful tool. Okay, it is representative of the test accuracies we will see. And essentially, there is this very nice characterization for a pair of PS rather than a set of PS, and finally get a tight bound for the generalization error characterization. But unfortunately, there is no free lunch. This so-called tight characterization is still an upper bound, and this upper bound, the quality of the upper bound needs to be evaluated more to understand how good it is. Okay, so that's, I think my takeaway about this paper. I'm not going to talk about the probabilistic bound over random data sets. I'm only talking about for one data set, right? So I leave that as an exercise to everyone to take a look at the rest of the paper. But before we move on to the next one, is there any questions? I wanted to use the maybe 10 minutes to introduce what I wanted to talk about next time. I know some of you haven't read the papers. So I wanted to first introduce the papers, and then you will have time to read it. But before that, maybe we'll use like 5 minutes to clear some confusions and questions we might have for this paper. Do people understand why I kind of arrange it this way? I introduced this empirical paper first, right, to kind of create a thinking of why there is a discrepancy, why statistical learning theory doesn't seem to work at all. And now using this paper, kind of clear out our confusions about these discrepancies and understand what is really not consistent between theory and practice, right? Any questions? This is a good time to ask questions.
I have a question for the previous slides. So I was just thinking about where is it possible that the summation here is also like, I don't think it's a big concern, but is it somehow a concern because actually dy can be large also?
Yeah, that's I think the dy essentially has it's actually very large, right?
Yeah, but I think maybe it's not that concern because if we are thinking about like the weights, they have a small norm, then I think it will finally will be like average out of like it's pretty small value even if dy is somehow large.
Yeah, so actually I think the computational complexity is indeed a concern in this bound here.
Yeah, because if k is different, then you basically have to compute all the things like from scratch. So yeah.
Yeah.
Okay, thanks.
Also, think about how we would want to improve generalization for during training. Have people thought about this? Right? You probably wanted to kind of minimize this upper bound, right? I mean, this is like an equality, but actually really is an upper bound because you have to use concentration inequality to get these, concentration terms, upper bounds. So when you use this upper bound, during training, you can kind of minimize those upper bounds, right? That's how people can improve generalization. Of course, whenever you are, at every iteration, you have a mini batch coming in and you try to do a stochastic gradient descent or ADAM or whatever optimizers. But when you do that, you might have a regularization term, which is this very expensive term. And what does that mean? It means that not only, this is a one-time cost, but it's that like the repeated cost of computing these generalization gap, right? So if you want to improve generalization, this is very computationally expensive. Laura is saying that anything requires knowing the expectation of the distribution is going to be a disadvantage. I don't think that's a correct way of interpreting this. Basically I wanted to say there's no free lunch. you were trying to characterize, you know, the difference between expectation and empirical observation, right? That's, you know, the nature of generalization era. It really, you know, it's like a philosophical question of which term you reduce this gap of, you know, the concentration deviation, which term you basically reduce all the deviation to, right? It seems like in this scenario, you're basically kind of deriving or reducing the deviation term to the deviation of the ZZ transpose as well as YK, YZ here, right? So you cannot avoid those expectations. Okay. All right, any other questions? Okay, let me move on to the next one. Okay, so I realized that I forgot to put this as a to-do list before, you know, the reading list for today's lecture, but I will first introduce the idea, and then, you know, when we won't have time to go into the details of this paper, but we'll talk about this paper next time in details. So let me first, how do I do slideshow? All right, so this is another perspective of understanding generalization. It is so-called a stronger generalization bounds for deep nets, while a compression approach. So it is using compression, but it's also a margin-based bound. So, you know, we've learned a lot about margins. We learn about margins when we want to understand the power of AdaBoost. Now here we will going to use the theory of margin as well as the compression to understand generalization bounds for deep neural networks. Okay, so again, there's this mystery of generalization ability of deep neural networks. The paper says like the mystery about the deep net is that they generalize despite having far more parameters than the number of training samples. Again, you know, this is like a discrepancy between a misunderstanding of like the statistical learning theory. So, you know, like what we've already seen before, they say one commonly voiced explanation is that regularization during training reduced the effective capacity of the net. And implicit, while use SGD, you know, some of the paper talk about that, or explicitly through weight decay or dropout, and batch normalization and stuff like that, as we talked about already. And the Zhang et al., like the first paper we read about generalization in deep neural network question, this received wisdom and field research in this area by showing experimentally standard architecture using SGD and regularization can still achieve low training error on random label examples. Okay, so we've already seen this. So then this paper is focusing on, you know, talking about an effective capacity metric. So deep neural networks trained on real life data have some properties that reduce effective capacity, but identifying them has proven difficult. You know, people have been using number of parameters, and apparently it is not a good indication of the capacity metric. Also, there is this flat minima discussion. We've already talked about it, right, last time. So indeed, you know, people have been showing that actually a simply using flat minima is not a good indicator of the capacity, because under some transformations, your generalization is not changed, but somehow your flat minima can become sharp, right? So then that basically means that's not a good indication. So overall, this paper is going to come up with a compression mechanism to characterize the generalization. So I don't have time to cover it today, but please go back and read this paper. Here is the archive link to this. I'm also going to upload the slides right after today's lecture. So I hope to see you, Thursday. Hope everyone's well prepared to discuss this paper. After that, if we do have time, if everyone is well prepared and we can have a quick discussion about this paper, then I hope to move on to adversarial examples in deep neural networks or robustness of deep neural networks. Okay? All right, thanks everyone.
Thank you.
Thank you.
Thanks.